It's my pleasure to introduce Sophie Langer, who is visiting us here from the Universität of Bochum, and she will talk about some statistical perspective on deep learning.
Thank you. Yeah, thank you for your introduction. Also, thanks to the organizers for this event. It's a great pleasure that I can present some of my work today. So the idea of this talk is that I'm not talking about one article of mine. I really want to talk a bit about the results that somehow shape the research I'm doing today. And then later I want to introduce some new frameworks, how one can analyze different prediction problems, and in particular image classification problems, yeah, with statistics. Okay, so before I start, I want to thank three great collaborators that were all colleagues in Twente: Johannes Schmidt-Hieber, Yuntong Cheng, and Insung Kong. Okay, and I want to start with the fact that Mateusz Telgaski told me a few years ago. He is one of the big names in the field, but he's quite negative about the development of theory. And he told me, and I think everyone agrees because it's just true, that deep learning breakthroughs were not driven by any mathematical understanding. They actually evolved despite the lack of it. And if you think about all the breakthroughs that we had in the last couple of years, diffusion models, LLMs, and so on, then also all these past architectures and training tricks were not developed by any mathematical or without any mathematical understanding. Okay, so where are we now? What is the conclusion? The main volume of work is phenomenological, which means that whenever there is a new phenomenon observed in empirical results, theorists try to jump on this problem and try to simplify it in a way to be able to deal with it theoretically and show something in these very simplified frameworks. So if you think about theoretical tractability versus practical relevance, where are we now? We are basically able to analyze feed-forward neural networks. If it comes to analyzing gradient descent routines, we're not even there, so we really have to simplify these networks even further. And so what happened in the last couple of years is that we are moving a bit in the wrong direction, because now we have methods that have a huge practical relevance. They're basically in our daily lives, but there is not really any theoretical foundation for that. Yeah, and then we come to the question, what is the impact of what we are doing? And first I would like to cite the godfather of AI, the Nobel Prize winner last year, Geoffrey Hinton, who is super negative about the development of AI. I think he actually quit Google because of that. Okay, he is quiet. I mean, we're all hoping that this won't happen. But at least there's also a long YouTube video of him where he's talking about all the risks that are connected to this very fast development of deep learning. And I think what is the biggest weakness is that we don't have any foundation why the method is suddenly working so well as it does. And with math, we are at least able to phrase it in a theoretical way. And in these very simplified settings, we are then able to get some indications, okay, why is it actually doing what it is doing? And while the gap, I mean, we saw this gap is too big to say, we are now, we are contributing to understanding it, but the step is very, very minor. But what is true for sure and what is happening right now is that different fields are somehow mixing. So if you think about optimization and statistics without analyzing the training routines, it doesn't make sense to analyze an estimator. So here really different fields have to start collaborating and talking to each other. And if you check archives, then you will see that basically on a daily basis, a lot of articles are published, and sometimes it's super hard to keep track what was already done and where are the gaps, because different fields have different languages, and it's super hard to understand if they did something similar. And I think if we really come up with a theoretical foundation, we are able to have a common language, and we probably also better structure the existing results. Yeah, and I think the last part, and this is maybe one of the big reasons why we're here, is that it's just fun analyzing these new models. Okay. Okay, now I need to sell statistics a bit. So what are the different aspects of deep learning theory? So roughly you can divide this research field in three different areas: approximation, generalization, and optimization. And in approximation, The goal is to understand the expressive power of these networks, so how well does the network approximate different function classes, and this is the field which is the best developed. The results are dating back to the 80s, 90s, where actually no one was really implementing these networks, so this was really a theoretical, out of theoretical interest to understand what is their expressive power. In generalization, we try to understand why does this method generalize so well to unknown new data, and in optimization, this is all about the training routines, some gradient descent variant or something like that. And what is nice about statistics is that we can model the prediction problem. So in the end, it's what is deep learning doing? It's, for example, doing image classification or something, so it's a prediction problem. And by formalizing it as a predictor, we can basically address all these three different parts. We can, but we're not able to do it right now because the tools are missing, but at least the framework allows us to dive into these aspects. Why is this the case? So if you think about a neural network estimator, and now I keep this R as a risk, so it can be anything for classification, it can be a misclassification error or something like that. And if I now want to come up with a bound to see, okay, how good is this estimator classifying, or how bad is it, how many misclassifications do we have, then we can decompose this error in these three different parts that I showed you on the circuits. Okay, and the first part is the approximation. You also see it here. So we have the best function, or we have this f star here, this g, which is the true function, and then we want to understand, okay, how good is in the end my estimator approximating this g, and so we compute the distance between this f star and g. In generalization, so this Rn is my empirical risk, meaning I'm just taking a risk over the training data I get. And then the question is, how close is it to the population risk? And then empirical process theory comes in, and we need to come up with some complexity measures here. Yeah, and the last part is the f star here is my empirical risk minimizer, so this is the best we can do. And of course, the training routine, because it's a highly non-convex loss landscape, will probably not end up in this minimum, and then we have to deal with the gap between these two estimators. Okay, and what happens in statistics is that we simplify it and we just say, okay, optimization, we don't care, we just assume it's ideal, so we consider an empirical risk minimizer instead. Okay, so we just say, okay, ideal, the gradient descent does exactly what we wanted to do. Yeah, and then the whole theory breaks down to these two different parts. Okay? And this is exactly what I want to talk about now. So I want to talk a bit about the past on approximation and then a bit on generalization. Okay, so if we go back to the 80s, 90s, then what people did is they didn't talk about depth. So they only said we take a very simple shallow neural network, meaning we have an input, we weight this input by these weight vectors beta. Okay, then there's another shift or bias vector gamma. This is our hidden layer after applying some activation function, which can be chosen up to you, basically, but there are some default choices for it. And then we weight these neurons in the hidden layer and get the output. Okay. Yeah, and again, what were the questions? How large is this function class? What kind of functions can be generated with it? And how does it, for example, approximate functions with specific smoothness conditions? Okay, and I think one of the very first properties that were analyzed is the so-called universal approximation property, which basically tells us a shallow neural network with a specific activation function has this property if it lies dense in the space of continuous functions. So up to some error epsilon, and in subnorm, it can approximate this function g. And okay, do I have it on this next slide? No? Okay. So the question is then, does this hold for any network? And one counterexample is that if you think about a polynomial activation function with some fixed degree r, and then you want to approximate some continuous function which is highly oscillating, then it's impossible to compute it or to approximate it with this polynomial activation function. So this is not fulfilling this property here. Okay, so how did they start showing that? They went to the one-dimensional case and tried to show in the univariate setting that this approximation property holds. And they used a continuous activation function, so it's a bigger class, And then one can indeed show that the network fulfills this property, and the proof is actually quite easy. What you need to do is you need to show that your network is able to resemble polynomials, and once I'm able to approximate polynomials, I can just use Weierstrass approximation theorem, because it tells us polynomials are dense in the space of continuous function, and then you're there. So it's kind of an easy proof. Okay, and then the question is, how can we go from one dimension to multi-dimension? Okay, we show this property in the univariate case, and then we do a detour via rich functions. And rich functions have basically the same structure as a shallow neural network, except that this Gj can now change. So instead of fixing one activation function, we can change it for every, this should be a J as well. We can change it for the different neurons in the end. And once we show that this, this function class fulfills this property, and we know that this is all, like everything, like every summand here is a univariate function, then we can use our result and we're done. Okay, that is one idea to do. Another idea where many of the results are based on, for example, a very famous result by Andrew Barron, is to use the representation of the function with the Fourier transform. So what are we doing? We have a Fourier transform, and then we take an inverse of this Fourier transform, and then we can just represent my function by a composition of the inverse and the Fourier transform itself. And if I then use that my complex, that a complex number can be represented by its absolute value times its phase, we can then plug this in, so we can represent our Fourier transform in this way. We plug it into the definition of this inverse here. So instead of this, we now replace it, because we're composing, we replace it by this. And in the end, because we only have the real part here, we get here a cosine function. And if I'm now discretizing this integral, I'm again at a shallow, so I have a shallow neural network with the cosine activation function. Okay, and then we had 2012, and suddenly everyone talked about depth. We all observed, okay, very deep neural network performs super good in practical applications, and then theorists try to understand, okay, what is actually the expressive power of these very deep networks? And they also fixed the activation function, because everyone observed the reload activation is the best. Okay, so this is just extracting the input itself, or 0 if the input is negative. Okay, so it's a bit the same definition as before. We are always weighting the input. We apply an activation function component-wise. We are weighting again, and we do this L times, and then we talk about a L hidden layer network. Okay, and these weight vectors that you see here, they can now be adapted to the data that we get, and this is basically what is happening during the training routine. So here we try to find the best weights for our problem. Okay, and I think it's a super basic result, but everyone used it for approximation theory. It's a result by Matouche, actually, who showed that if we take tooth functions, which have this form here, and we compose them as time, and take a sum over different compositions of this GS, then we can represent with this here x squared. Okay? And that was the first approximation result for depth, and I show you in a bit why this is so interesting. And this can be approximated by a deep network, because it's a composition of function, and this is basically the property of network. We are also composing different activation functions. So if we are able to represent one of these G's, which is possible with a piecewise linear activation function, then we can also represent this composition of it as time. Okay, why is it so interesting? Because if I can approximate x squared, then I can quite easily also approximate a multiplication by using polarization equality, because it's basically taking squared for the different components. And if I have a multiplication, I can extend that to multiplying not only two inputs, but d many. And if I have that, I can go from here to monomials. And once I have monomials, I also have polynomials. And if I have polynomials and I have a space with nice Taylor expansions, I have an approximation for smooth, in some notion, functions. So many of the results you see for approximation are exactly based on this idea, and this is why this x squared in the end was such an important brick in the whole analysis. Okay, so then remember I talked about approximation, and I said that the other component for the statistical results is generalization. And what are we doing in generalization? So in empirical process theory basically is we need to understand how complex is this function class. And there are also different notions of complexity, for example, covering numbers, or the Wapnick-Cherry-Nenkes dimension, the VC dimension, which tells us how complex is the function class. And there's a result by Peter Bartlett and co-authors who showed that if we take now the VC dimension of a network class with L hidden layers and R neurons per layer, then this can be bounded basically by these two components, by the hidden layers squared and the number of neurons. And what is happening now, so if you go deeper, this bound increases. And on the other hand, if I go deeper, I have a better approximation. So if you think about the two summations I had, we need in the end find this trade-off between these two terms and to get a specific bound. Okay, and basically all the results you see here are based on this idea. So people then try to come up with new function classes. You're, for example, running in a course of dimensionality if you not have a proper structure on these functions, but the really basic idea was dealing with these two components. And I don't want to judge them too much because it also includes my own work during my PhD, but of course they came with some restrictions. And I think they can be summarized in three different ones. So first of all, they all considered a non-parametric regression setting. Then they all analyzed very simple feed-forward neural networks. And this is something I said in the beginning, they all excluded gradient descent. So they all took an empirical risk minimizer. Okay, so why are these problems, these restrictions problematic? First of all, if you think about what kind of network structures are applied, then these are far from a feed-forward neural network. So I think I will show you that in some settings it actually makes sense to come up with a different network. And the other thing is, the empirical risk minimizer can be quite far from the true network that is trained after gradient descent. So the question is this really an informative thing to analyze in the end? Okay, and I want to talk about only these two things. So I am not talking about excluding the optimization. This is very, very hard. Okay, so what is a non-parametric regression setting? So in the end, it's a signal plus noise model. We have a functional relation between some input x and some output y up to some measurement noise epsilon, which usually has mean 0. Okay, and if we are now interested, so we take an estimator again for our G, and then we're interested in how good is it predicting the true labels in the end. Then we can do a decomposition of this error in two terms. On the one hand, we want to understand how close is it to this regression function, how good is it predicting this regression function, and the second term is something which is out of our control because it's the difference, or the squared difference, or the variance between my label and the function G. Okay, so this is basically the noise, or the variance of the noise. Okay, and I told you I want to talk about image classification, so why is it now problematic to have this framework there? Because if you think about images of one class, then there can be a high variety of different ways, for example, of writing down the digit 2. Okay? So these bounds, by using these regression bounds, the best we can do is we can keep this guy here very small by giving more data in. But this term here is out of our control, and if it's large, then it's in the end dominating our term, and so we don't get really an explanation why it's working so well for image classification. Okay, so we really need that quickly enough. This here goes also to 0. Okay, so this was one of the motivations why we said, okay, let's maybe come up with a different framework of analyzing image classification. And okay, the first question is what is an image? And it's basically nothing more than a matrix of pixels. And if you check a bit the literature, then in many papers it's written that it's a high-dimensional classification setting. Every pixel is an independent variable, and in the end we do function recovery in this very high-dimensional space, which means that if I'm now increasing these pixels, meaning I'm increasing my dimension, the problem becomes harder and the results get worse. But this stands a bit in a contradiction to what we observe also for us humans, because if you think about a highly resoluted image, then we're actually even better in classifying. So why is it suffering from giving more information having more information in the image? Yeah, and this was the motivation of saying, is it really a high-dimensional problem, or isn't it also a highly structured object? So what did we do? We said an image is a highly structured object, which means that I can represent my whole image by some unknown template function f, which is for each pixel evaluated at a specific location. And I'm now taking the integral over each pixel, so over each square, I'm now averaging this function. And if I'm now increasing the number of pixels, meaning I get more of these guys here, I get also more evaluation functions for evaluation points for this unknown function f, and one would now expect better performance. Okay, if we have a highly structured object, what does it mean? That different images of one class often rise due to different geometric deformations. And I think the simplest are scalings, shifts, rotations. Okay?
Can I ask a question?
Yeah, please.
What will you assume about the function class that f is in? And will you do PV functions, or are you going to put smoothness on f?
In the end, we need Lipschitz condition for f, but this is more for theoretical analysis. Yeah.
Because the question of how to describe edges and things is what is the right function class makes this quite difficult.
Yeah, exactly. Yeah. We thought about getting rid of this Lipschitz condition. I think it's possible, but it means a lot more technical steps, and so for us it was more coming up with this framework instead of
rotation.
Exactly. Yeah.
Thank you.
Okay. So we took these three different geometric deformations: scaling, shift, and rotations, and brightness. So we started with the representation of my pixels in this way, and then the three different deformations that we had is we have a brightness vector, which means I'm multiplying my template function with some eta, and by doing so I can have a lighter or darker version of this image. Then I have two scaling factors, psi and psi prime. Yeah, that help us to describe a smaller or larger image a larger object on the image, and we have two shift factors that can move the object on the image, or describe a move of the object on the image.
Sorry, one more question.
Yeah.
Is f real valued, or can you do R3 valued?
No, it's for two, like for dimension 2.
Okay.
Yeah.
Not the input, the output.
This is real valued. Yeah, it's
so
just real valued.
Monochrome,
No.
Not RGB.
No. Yeah. Okay, and then we submitted it actually quite a few years ago to JMLR, and they told us, okay, it's a nice idea, but it's quite a toy model, and it's not really interesting. So can you come up with something more general? And it took us quite some years actually. And in the end, we could replace these specific deformations by some invertible mapping A here. Okay, so this can now include, for example, different affine transformations. For example, it includes rotations because you can choose here this as a rotation matrix. But it also includes some nonlinear or local deformations by, for example, replacing these tau and tau primes by functions. And if you do that, you can describe also some locally deformed parts of the object. Okay, so this was our model, and then we wanted to do binary image classification with it. So we needed two different classes, and we are in the simplest classification setting, so only two classes, meaning that my labels is either 0 or 1. And what is different in the model is that, okay, each of these pixel values for each of the image can be described in the way I showed you before, with the difference that for the different classes we of course have also different template functions. So we either have F0 or F1. Okay, and we needed quite a lot of assumptions. So the first one is that these AIs, okay, they have considered as unobserved IID random vectors, and they're chosen from some deformation class A. We need that the object is fully visible on the image and that we have zero background. So every non-zero pixel really belongs to the object, and we're not allowed to halfly move it out of the image. So we really need to see the whole cat in the end. Okay, and this means in the mathematical framework that we have some assumptions on the support of our two functions, but also on the deformations, because if I have a very large image, then of course there are not many ways of moving it without moving it out. And yeah, this is why we have to put here some restrictions on that. Okay, so what is the goal compared to non-parametric regression? So before we try to solve a denoising problem, so we do some local smoothing in the end between the different points. And in our model, it's more about learning these invariances. So, I mean, in the end, these deformations are not informative for classification. So we want to come up with a method which actually ignores these deformations in the end. Okay, and we had two different approaches, actually three, but two can be phrased in a similar way. So we have a classification via inverse mapping, which is something not really implementable for practice, but more can be considered as a benchmark approach. So we wanted to see what is actually possible if we know the deformation class and what is optimal in this sense. And the second thing, and this is the relation to deep learning, is then we fitted a convolutional neural network to this problem, and I will show you in a bit why this architecture has some properties that help us actually to learn these invariances. Okay, so what is the classification via inverse mapping? So we assume this deformation class is known. We need that all the deformations are diffeomorphisms. And now we apply some operator on my image X, which is just a composition of a deformation B on my image. And if I'm now choosing these deformations B from the inverse of this deformation class, then I get transformed images, so I'm trying to basically rotate it back to the original one. And I'm doing this for each training image, 1 to n. And then for the new test image, I'm doing the same, and I'm taking the one nearest neighbor in this transformed space. This is then, so the label of the one nearest neighbor is the label of the new image. Okay, so what can we show? We need that the labels of both, that at least we see one image of each label. It doesn't need to be balanced, but at least we need to see it once. We need this assumption on the template functions that they are Lipschitz, and we have a minimal separation condition between the two different template functions, which means that they shouldn't be too close together to still be able to distinguish between the classes. I will talk about this lower bound in a bit. Okay, and if we have if we fulfill these conditions, then we can show that this estimator, this one nearest neighbor estimator, perfectly recovers the labels. But of course, this problem is quite heavy to solve because you have infinitely many deformations probably. So we could also discretize this set. We can get the same result, but even discretizing means if it's a complicated deformation class that it's still quite heavy. But if we really have these special deformations, we can do something simpler. And okay, we're coming back to the model I introduced in the beginning. So we only have scaling and shifts and this brightness eta here. And if we have this, then we do something very simple. So we have zero background. So we can find the smallest rectangular support around our image. So we find the smallest rectangle, which still includes all the non-zero pixels. And if we have that, we can use this frame and map it back on 0, 1 squared. And if we have this, we are already invariant to any shifts or scalings. And okay, in the end, we normalize our pixel values to also get rid of the brightness. Okay, one slide is missing here apparently. Okay, for this estimator, we can now do the same. So we can also take a one nearest neighbor estimator, just replacing this operator now by this method I showed you, and we can get the same results in the end. So we also perfectly recover the labels. Okay, a bit about the lower bound. So if we have a lower bound on our two template functions that is only 1/28D, then one can show that my pixel values can either represent by one of the template functions or the other. And if this is possible, of course, we are not able to distinguish between the classes anymore because we don't know is it belonging to this one template function or the other. Okay, so that was our benchmark approach, and the second more interesting one was to deal with convolutional neural network. Who knows about convolutional neural networks? Who heard about it or at least hasn't? Okay, so most of you. Okay, just very quickly, so what is the biggest or the main ingredient for a convolutional neural network? It's basically the convolution. And what is happening during this convolution is, so we apply a small filter that you see here, and this filter is now sliding over the image, so it remains fixed for the whole sliding process, and at each position where it stops, it's computing pointwise the weight, so the entry of the weight matrix and the pixel that is covered. And then they are added, so it's a sum of a Harderman product in the end. Okay? And if we do that, we get a convolutional or feature map. And in each of the convolutional layers, we not only apply one filter, but we apply several. And then we get also different feature maps in the convolutional layer. And usually after a convolutional layer, a pooling layer follows. There are different ways of doing pooling, but often that means that it reduces the dimensionality because we are basically grouping together different pixels at a local position. And after convolution and pooling, so this can happen now several times. If we talk about deep convolutional neural networks, then we have the last component, which is a fully connected neural network. And the main idea of this architecture was that we are probably able to extract some high-level features by having this fixed filter sliding over the image, for example, detecting the ears of the cat or something like this. It's a bit heuristic behind it. Okay, so what does it mean from, like, how can we phrase that mathematically? We take, again, a simplification, so we only have one convolutional layer. We fix our activation function to be the ReLU function, and we apply k different filters, W1 to Wk, which means that if we do now these convolutions that I just described before, which I'm now notating here with this star, then I get k different feature maps. Okay, and on these k different feature maps, I'm now applying pointwise my ReLU activation, and then I do hardcore pooling. I just extract the maximal value of each of the feature maps. Okay, so I get in the end a k-dimensional vector. Okay, so I'm just taking the feature map, extracting the maximal value. Okay, so that means for my fully connected network, the input dimension is k here. Okay, and then I'm taking exactly what we already had in the beginning. I take an L hidden feed-forward hidden layer network with the difference that because we want to do classification, we in the end want to extract probabilities. So we are mapping the input between 0 and 1 by applying softmax activation. Okay, so this was our architecture, and I now keep one variable. I only have one variable, and I can describe the whole architecture with it. So I have this M, and I need 2 M convolutional filters in my convolutional layer. I do this global max pooling, and in M I then have a logarithmic depth of fully connected networks, and my output is two-dimensional because we extract the probabilities for both classes. Okay, so what is one nice property of convolutional neural networks is that they are nearly invariant to shifts. So it doesn't matter here if my object was on the lower left, lower right, or upper left corner. We have the same filter for the whole sliding process. So we will get the same signal in our feature map, just at a different location, but now we do this global max pooling, so for us it doesn't matter where it was, and yeah, we get the same result basically. So one of these deformations basically just solved by this architecture properties of the CNN. And then the question is, can we also come up with some scale invariant or rotation invariant network? There are ideas, for example, of the group of Maxwelling, where they try to come up with equivariant CNNs that are group invariant or equivariant to group actions, but it's a bit of a debate in the literature whether this is desirable or not.
Does the invariance require a constant background? Is that why you say nearly?
Yeah, so it's still, this is all 0 actually, so it should be black.
And if you make it periodic, does that help?
Periodic in...
If you make the image periodic, so when it shifts off the right-hand side, it would come back in. Put it on the tour.
That's a good question. Huh, I haven't thought about it. Yeah, probably that would help. I mean, we have basically filters for different deformations in the end. So... I would need to think about it, but it's an interesting idea that we're not losing information, we just have it at a different position in the end, yeah. Okay, so we take a supervised learning framework, we have again images and corresponding labels, and the first step is to get rid of the brightness again, so we normalize our pixel values. And now we need to come up with a loss function to find the best CNN in our class. And the first idea is we take 0, 1 misclassification error. So we just count the number of misclassification our network generates. And okay, we want to minimize that. So whenever there is so we want to keep the amount of misclassification small. And you see this is an empirical risk minimizer because usually here now the gradient descent routine would jump in and we take the simplification of an ERM. Okay, so 0, 1 loss or minimizing 0, 1 loss is NP hard, so can we do something better? And yes, we can replace also this loss function by some surrogate loss, and for classification, the default choice is cross entropy loss, so we can also minimize just this log loss, this log loss. Okay, and once we have an estimator for these two probabilities, we then just do a plug-in classifier, and so we extract the label 1 if my probability that it belongs to label 1 is larger than 1/2. Okay, so what are the different ingredients in the end? So we need that the object is fully visible. This M that I showed you before is now depending on the complexity of my deformation class. For example, if you think about the class of only shifts and scalings, the shifts are just done by the network. So this complexity now has only 2 things that we need to discretize, the psi and psi prime. So this is a d squared in this setting. For rotations, we get another rotation angle, so this becomes a d to the 3. Okay, we again need that the template functions are Lipschitz, and we have this again the separation condition between the 2 different template functions. Okay, so what is then the result? The misclassification error of this plug-in CNN estimator can then be bounded by this term. So n is my sample size, and my m here is this complexity of the deformation class. So again, we have a bit the dimension d here as the bad cop, because if my deformation class is complex, then this d becomes larger, okay, and the rate becomes worse. But what it also means, if we have, for example, a higher d, then these 2 template functions can be closer together. So at the same time, we are then able to distinguish between classes that are probably a bit closer together than we have it for smaller resolutions. Okay, so a bit about the rate. So we don't have a lower bound for that. So it's likely that it can be improved. We are right now thinking about doing a lower bound, but we haven't solved it. Then there is a big part of it, because remember this decomposition I showed you in the beginning is approximation theory for CNNs. And the first question is, how can we use these separate filters to learn deformation? So how can we choose the weights in these filters? And what we do in this fully connected layer is we just learn a maximum function of these k components. Okay, and the last idea we have, which is not solved yet, is that one could use now this deformation model and apply it to my data before I start training. So I augment my data with this model, which would mean I can reduce the number of real-world images and instead have these artificial images. We could reduce complexity, but this comes at the price that we have some dependencies in the data because everything depends on the original real-world images then. And so we can't use this statistical theory around IID data because we need to at least bound a bit what is the dependency here. Maybe it's a mild dependency and then we can carry it through the whole analysis. But yeah, this is not solved yet. It's just an idea we had. Okay, do I have time for... Yeah, okay. Okay, so the second thing I want to talk about is about, again, approximation theory, but the question is a bit, so where do we go next? So if you think about how these different activation functions evolved over time, then in the 1950s, we started, or even earlier, we started with the perceptron, which is only one neuron, which extracts either 1 or -1. Okay? So okay, it's a shifted Heaviside function. So we could also say it's 0 or 1 here. Okay, then we had the 80-90s. We had these smooth activation functions. We tried to analyze these different properties. For example, this universal approximation property. And then because of these great empirical results in 2012 around, we had redo activation. And now I learned that there are different ways of, for example, smoothing out this 0 here, so there's GLU, and there are many, many other ideas of changing the activation function. So the question is now, should we now jump whenever there's a new activation function on it and try to do some approximation theory for that? Or, and this is what we did in this project, let's go back to the roots and try to understand what are actually the approximation properties of Heaviside networks. Why is this interesting? So, okay, particularly in Twente, we are now talking, or we talked about, now I left, but they're talking quite a lot about biological inspired learning. So biological neural networks. These networks have a completely different property because these neurons are functions that evolve over time. But in this very simplified setting, you could think about, also in the brain, about an all or none firing, which means that this resembles a Heaviside activation. And also for these Hopfield networks, so this is the second Nobel Prize winner of last year, we have this Heaviside activation as in the architecture. And okay, if we talk about energy efficient AI, then okay, we only extract bits by the Heaviside function, so it's it needs a low memory. And for training, one could, for example, use some local update rules. Okay, so what is my definition of a Heaviside neural network? Basically the same as I had it before. So I have a number of hidden layers L and a number of neurons for each layer, which is my width vector K. So we have the same definition with the difference that now this activation function here is replaced by a Heaviside function. Okay, and I'm summarizing this whole function class now by DHN, L, and K. Okay, so if we think about the expressive power, the first thing that we notice that every neuron after one hidden layer is either extracting 1 or 0. So if you think about the one-dimensional case, what is happening in the first layer is that we get a piecewise constant function, okay? And the amount of pieces is at most the amount of neurons that I have in this layer. Can be less, but it can be at most this amount, K1. So the question is, how can we now approximate, for example, a continuous function? And what we can show is that, that we can't be better than something 1 over 2 times K1 plus 1. And K1 is the amount of neurons in this first hidden layer. What does it mean? That in this bound we see that depth is actually not helping at all. So we don't have any of the other Ks in our bound. The proof is pretty easy. So first of all, what we can do is, or what we do is we restrict our function on a segment, meaning we only evaluate it between x1 and x2. And if we have that, then okay, we realized on this segment, this is exactly this plot I showed you before, we get a piecewise constant function after one hidden layer with k1 plus 1 pieces. So this means deeper layers do not increase this amount, but if we now go to some layer L, then this layer is only extracting kl minus 1 plus 1 different pieces, because it depends on the information that we had in the layer before. That means that if we are in the same piece, so my x lies somewhere here, then we get for both inputs the same output. But this means that the approximation power of my network can basically reduced to taking f as a piecewise constant function over these k1 plus 1 pieces. And this here can then be bounded by this 1 over 2 times k1 plus 1. Okay? Okay, some remarks on this bound. We can show tightness of this bound for specific functions, for example, for rich functions, where we again apply some affine transformation on some G0, or if we assume again some Lipschitz condition on this function. So then the question was a bit, why is that now interesting? So why should we talk about depth if we are basically losing everything after one layer? And then we can either completely stop this project because it's apparently not very expressive, or we need to adapt something. And why? What was a bit the motivation? Deep Heaviside networks have some properties that the shallow ones do not. For example, if it comes to representing this XOR function, then this can't be represented by only one hidden layer. So we really need 2 hidden layers to do this. So this is at least one of the advantages. And also when it comes to approximating hypercubes, we can do that in a deeper layer, but not only with one hidden layer. Okay, so we needed some adaptation, and what we did is we included some skip connections. That means that my network has at different layers, again, access to the input. Okay? So this means for our notation, we get another component in our network architecture, which are these S's here that represent now the amount of skip connections that we have in the different layers. And of course, these skip connections started as 2, because for S1 you just get the input as the input, for the first hidden layer. Okay, so again we wanted to first show a lower bound, and if we now have these skip connections, we indeed see that my lower bound gets better in a sense that it's gets bigger if we have depth. So even if we only have one skip connection, so only one neuron becomes this or gets this information of the input, then we get here a 2 to the L. So with depth, this rate decreases. Okay. And if you now remember what I said about approximation property of ReLU networks, then we saw that, okay, everything started with x squared, and then we could do also polynomials in the end by following these different steps. So we wanted to also come up with a fundamental idea of approximating x squared, but of course, the approach we saw with the sawtooth function is not working with Heaviside networks anymore. So the question is, what could we do else? Okay, and we can show that looks way more complicated than it is. So we have this network class with the skip connections. These skip connections, okay, I now choose my amount of neurons I have depending on the skip connection. We don't need it, but it's a bit nicer to see it now in the bound. And if I have this, I can show that I can approximate x squared by basically the lower bound that you saw before, with the difference that we don't have a 2 here. Okay? So up to this factor 2, we get the same. And if we now plug in for k1 this s, the rate becomes basically s plus 1 to the minus l plus 1. A bit about the proof. So what was our idea? The first step is that we can represent X in a mixed radix numerical system. For example, base 2, or we can really mix it. So we don't need to fix the base. So then we have these different bits, and this is nice because with the Heaviside activation we can basically extract these different bits, and we can now pair these bits to in the end do a multiplication. Okay, and then we get exactly this X squared by doing this bit extraction for X. Okay, if I'm now comparing the bound that I have to what we have with ReLo, then we see if I have only this one skip connection, my error has this size if I have quite a high amount of parameters. So for this bit extraction, I need a lot of neurons, and if my precision gets better, then these parameters explode. And if I compare this with the ReLo activation, then the ReLo activation only needs a very limited amount of neurons, so we only need a width of 2 to get a precision of epsilon, so we have 1 over epsilon neurons in the end that we need. However, what is nicer about the Heaviside network is that what I said in the beginning, we only need to transmit these different individual bits, and this can happen with fast evaluation and less memory. Okay, so what did we do else? So we came up with this fundamental step of X squared, and then we can follow the same path as with the ReLo activation, and in the end can do something for Hölder-Smooth functions. So we do again this approximating with polynomials and get these rates. The other component that we also had for these risk bounds for ReLo networks is that we need to find a VC dimension bound for Heaviside networks, and the connection between VC dimension approximation, the VC dimension gives us a lower bound of the approximative power. So here we also could build this relation. Okay, if we have these two components, we can then also derive statistical risk bounds for a network estimator in a non-parametric regression setting. And we had another idea of, instead of having skip connections, we could also have linear activation functions. This is more or less the same, because with a linear activation function, we can also pass through information without any error. Okay, so what's next? That is a bit the question. So if we talk about this Heaviside networks, then we could now talk more about biological inspired learning, for example, also about spiking neural networks, or we also have different optimization schemes here, for example, zero-order optimization. And what we see now in the theory of large language model is that there are quite some talks, at least I saw quite some talks last year in the US, where people were more talking or trying to analyze the algorithm. So they put in some task for the LLM and try to understand when is it, where's the bug, so when does it start to hallucinate, for example. So the problem, it shifted a bit from the approach. Yeah, and I think this is more a philosophical question. So what is still the purpose of theory? I think right now we should just accept to stay phenomenological, because we can't be faster than practice. Yeah, the question is, can we still give some intuition? And right now doing a project together with some guys from the US where we just want to understand or come up with some challenges for the future. And what we realized is that, for example, if we talk about these limit regimes, we can maybe, I don't know, have different scaling regimes to understand, okay, what different architecture or what different initializations can give a hint for different performance, and that could be at least one bit we could also offer to practice. And yeah, this is very important to me. I mean, we really need to cross our boundaries, because this field forces us to connect with other research fields, and we should have this openness to really do that. Now I'm quicker than I thought. Thank you for your attention.
Right, thank you very much for a nice talk. Are there any questions?
These are the references for the two papers.
Are there any questions from the audience here?
I'm just wondering, so the advances in, everyone kind of understands that there are improvements.
Yeah.
And in the theory, we kind of analyze them in quite a classical way. We say an optimization algorithm converges almost surely to a local minimizer. We have decreasing approximation error. But in some sense, are we trying to come up with explanations for the improvements? And instead, is there any scope to kind of look at different theory? You know, and I know that happens in the optimization literature. We look at the types of minimizers that we converge to and their generalization properties, but you know, it seems like we're still analyzing them in quite classical ways, and I was wondering what you thought about that.
Yeah. I mean, this is a bit what we also try to understand in this project. So, is it a good approach to jump always on these empirical observations and then I don't know, try to understand a bit? I don't know. I mean, it's hard to have a different viewpoint on it. So I can't give you a clear answer what would be a different approach to do theory around that.
No, thank you.
Any other questions?
Thank you very much for a very good talk. Can you hear me?
Yeah.
Have you already thought about analyzing generative networks for images, for example?
So you mean, for example, diffusion models or generative?
Yeah, or variational encoders or something.
So yes, I'm having right now a project on latent diffusion models. I mean, there are some statistical results on, in the end, also risk bound. I mean, it's a density estimation problem, these diffusion models. And then a big step is also approximation theory for the score function. And we try right now to do it on a latent space, which means that we first have an autoencoder that maps on a lower dimensional space, so then we run the diffusion and then we map it back. That is one idea I'm right now working on, yeah. But there is a lot of ongoing research in this field, so it's kind of dangerous to start it because there are probably people that are way quicker than I am.
Are there already results?
I mean, there is this from statistical theory. I know this result by Taiji Suzuki and Kazusato Oko, and based on this result, there was quite a few extensions or different assumptions on the density. But I think there's more for different aspects of diffusion models. Again, I'm not completely familiar with the whole field. Yeah.
Please. Yeah.
I have a question about activation functions and how, do people consider radial basis functions as mainstream activation functions, like in the radial basis neural network world?
Basis functions.
Gaussian kernels, basically.
Yeah.
I don't know. I mean, you mean as activation functions?
Yes.
I honestly don't know if people are doing that. No idea.
Thank you for the great talk. In your work on the deep heaviside networks, you're concentrated on theory of approximation, and it's very interesting the thing you showed with the skip connection. You did not work at all on the training side, on the learning side, right?
Yeah.
So, I mean, do you think that people are currently looking at how to train this network? Because
so in Twente, I mean, Johannes Schmidt-Hieber got this ERC grant on this this idea of biological inspired learning, and one part of his project is also on zero order optimization. So he's doing something on that, and also tries to understand what is. I mean, one wouldn't expect better performance than for gradient is the first order optimization, but they have some papers on that, on forward gradient descent. He did also something. So if you check a bit what he did, that is at least one research group, but maybe there are more that are now diving into that. Yeah.
Maybe just checking if there are some questions from remotely or remote. Doesn't seem like it's the case. We have a question live. I mean,
Thanks so much for the great talk. So I'm not a theoretician, so I may have misunderstood something. But in kind of the modern neural networks as we train, we get the training error of 0, right?
Yeah, yeah.
How do you account for that? Like, can you explain why this is happening?
I mean, this whole theory around overparameterized networks, right? And then this benign overfitting in the end. So what wouldn't work in this decomposition I showed you is that, remember this VC dimension, this will explode with this approach. So I mean, there are results on linear regression, something like that, where they show that there is an implicit regularization effect happening. I think here we really need to also include this optimization scheme, because even if we're in this highly overparameterized regime, what gradient descent does is probably happening on a smaller dimensional space, so it's probably only like the weights that I learned are lying probably on a manifold, and then we can again deal with the complexity. But with this, taking an ERM over an overparameterized network wouldn't work, because then you get just a bound of infinity. Yeah.
So I guess my real question is it time to move away from this bias variance decomposition? Because like you don't have to do SGD to get that, right? Like we see that in linear models. Random field features, like you get that without SGD, right?
Yeah,
so, like, is it maybe time to kind of develop on this?
I have, at least this is a bit what I see in the literature, I have the feeling this happened in like early 2020s, that we did this, that we have these results on benign overfitting and so on. Not from a practical point of view, they're still doing it, but from a theory point of view, they try to understand it in these super simple toy models, but then something else happened, like diffusion models, and suddenly no one is really doing it anymore. But yeah, there are many, I think they only did it for kernel methods or so, and also there are not too many convergence rates existing. So there is a huge gap in understanding that, and then we have to move away from this ERM and this bias variance trade-off. Yeah, no, you can. I think it's a good criticism that it's not super informative compared to what we have in practice. Yeah.
We're slightly out of time, but I can't really hold back. Is there? I also have a question. Is there any way to incorporate some sort of hierarchical? The fact that the functions you're trying to learn are not just any generic function, but they have this hierarchical structure. So you're trying to learn a picture. Well, a cat has eyes and ears and mustache and stuff, and then the network maybe that's what it learns. And so, I mean, what you presented is very general, but is there any way to embed this sort of idea about the class of functions you're trying to learn into this framework, do you think?
So I did something with this hierarchy if we go back to this pixel-wise approach, because you can, for example, assume some structure on the upper story probability in the end that you try to learn. And then you can say, okay, actually not the whole dimension of the whole image matters, so we group them locally, and then we use this hierarchical structure to, in the end, embed all the information.
But you do it by hand in a way, right? I mean,
you come up with a model that we then call hierarchical interaction model. Yeah.
Okay.
Yeah.
I see. But then there's no way you can. Is there a way you can see the network doing that automatically in a way, or learning that class of functions automatically?
I'm not sure what you mean by automatically. I mean, in the end, it's doing that, because given that this structure exists, the network is automatically doing it, because we can just use this compositional structure.
I see. Okay, so the fact that you have
represent the different bricks. Yeah.
Okay. Thanks. Okay, great. So if there's no further questions, let's thank the speaker again.